In this lesson, we're going to introduce a new type of function that we've actually already laid a bunch of groundwork for. So we've done a lot of the work already that's going to make this pretty easy to understand, I think. These types of functions are called accumulation functions, and we're going to imagine ourselves as the owner of an umbrella factory here. So what we have here as we read the text is my function g. I'm going to annotate that as g of t. This is the rate at which umbrellas are being produced, right? So it's a rate given by g of t, umbrellas per hour, in hours after the factory opens in the morning. Okay, so there's our context. And what we're asked to do is estimate roughly how many umbrellas were produced before we arrived. And we arrived at 9 a.m. because we're the boss and we can sleep in if we want. We can spend all the time in the world eating breakfast if we want. It's important to note here 9 a.m. is... If we opened at 6 a.m., 9 a.m. is t equals 3, right? So we're looking at this value here. But if you said about 50, we would be wrong, right? Because remember, this is the rate at which umbrellas are being made, and we want to know how many. So in other words, we're looking for the total. Well, one thing we might do to guess, right, would be we might take the average rate over those 3 hours, right? So we might take g of 3 plus g of 0 over 2. So here's our average rate. We multiply times 3 hours. That might be a good estimate, right? Well, this would end up being g of 3 would be 20 times 3 minus 3 squared, which is 51. G of 0 is 0, which is 76.5. Which means the answer to my question is about 77 umbrellas that we made. And then again, we did that by taking the average rate at which we produce things over these 3 hours and multiplying by 3 hours that we were counting, right? And that's how we got that estimate, which is a pretty good estimate, I think. Now, interestingly enough, if we look at this estimate graphically, well, here are my points, g of 0, g of 3. What I've done here is I've just used a trapezoidal sum to estimate the area under the curve. So here's my 3 hours that I multiplied by, right? This height was 51, this height was 0, and I multiplied by 1/2 because we're using a trapezoidal area, right? So this function, right, if we have a rate, we already know that the total is going to be the area under the curve. And the expression for the exact number of umbrellas would be, well, the integral from 0 to 3 of g of t, we called it, which would be the same as the integral from 0 to 3 of g of t was 20t minus t squared. So again, we already laid the groundwork for this. The area under the curve is represented by the integral, and the area under the curve in this case gives you the total number of umbrellas we produce. So then as we look at number 2 here, if we want the total number of umbrellas until our lunch break, well, 12:30, let's see, 12:30 is 6.5 hours after we started, and that would be then the integral from 0 to 6.5 dt, and if I wanted I could substitute in that expression. And a function then, f of x, that gives the total number of umbrellas produced x hours after the factory opens, well, if we follow the pattern, we have 0 to 3, 0 to 6.5, 0 to x, my integral is going to be. And then the integral of g of t dt. And that's going to be, so this here is my accumulation function. So this is f of x, and it takes x as an input, and its output is the area under curve g from 0 to that x value, right? So here's an example of the types of area we're considering. And this function is what we're studying in this module. So this is my accumulation function. So really it's just a function with an integral inside of it. You can think of it like that. Notice we have two different variables going on, which is interesting. We have f of x is the integral from 0 to x, and then my inside function, we're using t's here. So we have t dt. It is important that your notation is correct. So you want to match those variables. On the inside of the integral is t here. The outside is x. But it's not really going to change your reasoning much, so don't burn a lot of brain power on it. Okay. F prime then, if f of x is the total number of umbrellas, f prime of 8 then, as for an interpretation, is the rate that we're making umbrellas at t equals 8. Okay, so our interpretation of the derivative hasn't changed. Notice here, this is actually really interesting. This was a rate. This is the exact same interpretation of g, right? That makes a lot of sense. So f prime of 8 would be equal to g of 8. And if we wanted to know what f prime of 8 is, it would be equal to 20 times 8 minus 8 squared. So in other words, I'm plugging it into g. I think that gives you 96 umbrellas. Okay. And then the last question here, this is where we really solidify our understanding of how this connects to the graph. When is the number of umbrellas produced growing the fastest? So we have to do a little bit of thinking here. Growing the fastest means our derivative is at a maximum. So f prime of x should have a max. Well, if we go back and look at our graph here, there it is. So that would be at t equals 10 because f prime has a maximum. And notice we didn't do any setting of anything equal to 0 as we have in the past, because the question just kind of directly asks us about this graph we already have. It wants a maximum rate. Well, the graph is already the rate up here, right? So that's the intuition. On the next page, we're going to consider just a really quick example of how we use this notation in practice using a graph. All right, so here's our graphical example. So we're given f of x is the integral from 3 to x of g of t dt, and then notice the graph that we're given is the graph of g. So I would always annotate what your graph is, because if this was g prime, for example, it would change our reasoning a lot. All right, so if we want f prime of -3, well, by the same logic as the previous page, right, f prime, we can almost think of it like this, right? So if we take the derivative of both sides, and this is kind of ugly notation, but I think it'll get our point across well. If we take the derivative of both sides, the integral and the derivative cancel out, right? So this really just gives you, and again, this is not perfect notation, f prime of x equals g of x. So in other words, this is just asking you for the y value, right? So f prime of 3 is equal to g of 3 is equal to, and then by that same logic, if we have f double prime, well, that's the same as g prime of -3, right? And g prime of -3, well, that's going to be the slope, which would be rise over run. And then I saved the plain old f of -3 for last. And the reason I did that is because I picked a particularly tricky one here. So here's again my f of x. So f of -3 would be just very simply the integral from 3 to -3 of g of t. And the reason this one is tricky, we haven't really run into this much before. The reason this is tricky is because my bigger value is on the bottom, right? So this integral is actually going from 3 to the left to -3, right? So my first step here is going to be rewrite this in kind of a more proper way. It's kind of like an improper fraction, right? We can use a property of these things, which just says if I negate the whole thing, I can switch the bounds of integration like this, right? So notice I've switched now -3 to 3, and I've added a negative in front, okay? And then my integration then is just the area, right? So we have this area and this area if we're going from -3 to 3. So here my height is 2, my width is 3, and then here my width is 3, and my height is 3. Right, so I would have, then I'm going to keep the negative in front. My first triangle is going to be 1/2 times, my height there was -2 times 3. And then my second triangle, 3 times 3 times 1/2. And then I add those areas and I negate them. And again, that negative comes from flipping the limits of integration there.